Aditya, a word that conjures pride and awe among Indians. A word that today is synonymous with technological know-how, cutting-edge science, and being at the frontier of human knowledge. Aditya means the sun or the newly risen sun, Lord Surya or Lord of the Sun. Appropriately named, Aditya L1 is India's first spacecraft to study the sun exclusively. India's indigenous polar satellite launch vehicle, PSLV C-57, was used by ISRO to successfully launch the satellite on September 2, 2023 at 11:50 IST. It was yet another success of ISRO, close on the heels of the very successful landing of Chandrayaan-3 on the lunar South Pole. While two ISRO projects, one after another, executed to copybook perfection, made Indians very proud, it also placed India in international reckoning with regard to our prowess in space technology. The world sat up and applauded. After a long journey of 126 days through raw space, Aditya was successfully placed in a halo orbit around L1 on the 6th of January 2024. It is now ready to perform its scientific targets at understanding the sun and its phenomena along with facets of space weather. Coming to the spacecraft Aditya L1, the postfix to the name Aditya, L1 is a point about 1.5 million kilometers away from the Earth, between the Earth and the Sun, much beyond the orbit of the Moon. Let us understand a little more about this point. First, L stands for Lagrange, after Joseph Louis Lagrange, an Italian mathematician and physicist. This picture shows the different Lagrange points around the Sun. The natural question that comes to the mind is, what are Lagrange points? Lagrange points are positions in space where the gravitational pull of two large masses precisely equals the centripetal force required for a small object to move with them. These points in space can be used by spacecraft to reduce fuel consumption needed to remain in position. Simply put, a spacecraft placed at any of these 5 Lagrange points will have the same orbital period as the Earth. To understand this a little better, let us look at the planets of the solar system and their orbital time periods. Mercury, the closest to the Sun, has a time period of 88 days. Venus takes 224.7 days to go around the Sun once, while the Earth takes 365.25 days. And going farther out, Neptune takes 60,148 days or 164.7 years to complete one revolution. Clearly, the nearer the planet is to the Sun, the shorter the time period, and the farther the planet, the longer the time period. Now, look at this picture again and focus on the positions of L1 and the Earth. The point L1 is nearer to the Sun by about 1.5 million kilometers than the Earth, and should have a time period shorter than that of the Earth according to the pattern we just saw for the planets. But a spacecraft placed at L1 has the same time period as the Earth. Again, at the point L2, the time period should be longer than that of the Earth, but actually the time period of the spacecraft at L2 is again equal to that of the Earth. This is the same at points L3, L4 and L5 also. Why does this happen at these special points? The centripetal force required to keep a spacecraft in stable orbit depends on the strength of the gravitational field, that is, the gravitational intensity at that point. Nearer to the Sun, the gravitational intensity is stronger, depicted by the gravitational intensity lines drawn closer to each other. At these points, the centripetal force required is higher, and thus, at these points, the time period is shorter. The point L1, in spite of being nearer to the Sun than the Earth is, has a gravitational intensity equal to that at the Earth. This is because the higher intensity at L1 due to the Sun is partly cancelled by that of the gravitational field of the Earth acting in a direction opposite to that in which the Sun's field is acting, making it equal to that at the position of the Earth and hence an equal time period. While at L2, the Earth's gravitational field adds to that of the Sun, and so, in spite of being farther away from the Sun than the Earth is, at the point L2, the time period is equal to that of the Earth. Point L3 is at the same distance as the Earth is from the Sun, and so has the same time period. To understand the physics of L4 and L5 requires the mathematical solution of the restricted three-body problem, which is beyond the scope of this presentation. Now that we understand what the Lagrange points are, let us have a quick look at the different payloads or instruments that Aditya L1 is carrying. As you can see in the table, there are 4 remote sensing payloads and 3 in situ payloads. The different functions that these payloads are designed to perform are corona imaging and spectroscopy, which involves studying the corona of the Sun, photosphere and chromosphere imaging, narrow and broadband, which again involves studying the photosphere and chromosphere, soft X-ray spectrometer, which will study the Sun in the longer X-ray wavelengths, and hard X-ray spectrometer, which will study the Sun in shorter wavelength X-rays. The 2 solar wind and particle analyzers will study the composition of solar wind, that is, the protons and heavier ions, and the lighter electrons along with their directions. And the advanced triaxial high-resolution digital magnetometers will study the in situ magnetic field in all 3 spatial directions. But why do we need to study all these aspects about the Sun? How will this knowledge help us? How important is this knowledge? To better understand, let us have a look at some of the relevant aspects of the Sun. The solar corona is a faint region outside the surface of the Sun, which is visible only during a total solar eclipse when the bright light from the photosphere of the Sun gets blocked out by the Moon. The strange thing about the corona is that while the surface temperature of the Sun is about 5000 degrees centigrade, the temperature of the corona is about 2 million degrees centigrade. And I thought, if you walk away from a heat source, it should get colder. We need to understand this puzzle. The Visible Emission Line Chronograph (VELC) payload will help us to study the corona and perhaps find an answer to the intriguing puzzle. The photosphere is the surface of the Sun. It is the lowest layer of the atmosphere of the Sun. It can also be described as the innermost layer that can be directly observed. While the chromosphere is the second layer of the Sun's atmosphere located between the photosphere and the corona. It is a thin layer of plasma that extends for at least 2000 kilometers. This layer is also hotter than the photosphere, though the photosphere is nearer to the Sun. Understanding the 2 layers will help us understand the Sun's rotation, its atmosphere, Sun's density, and surface dynamics, as also the Sun's influence on the Earth. The Solar Ultraviolet Imaging Telescope, or SOOT in short, payload, has been specifically designed for the purpose. Moving on, the Sun has an 11-year cycle of activity. Every 11 years, its activity reaches a peak called solar maximum and then slides down again. What kind of activity is included in solar activity? The two primary activities relevant here are magnetic activity and X-ray activity. During this period, there is an increase in solar storms like coronal mass ejections and solar flares. The current cycle, solar cycle 25, the 25th since 1755, when extensive recording of solar sunspot activity began, will be at its peak between the months of January and October 2024, then gradually slide down and again peak around the year 2035. To study the increased X-ray activity, the Solar Low Energy X-ray Spectrometer, SOLEXes, and High Energy L1 Orbiting X-ray Spectrometer, HELIOS, payloads have been included. While the Sun has always been a source of energy for us, it has also been a source of awe and wonder. But did you know that it can also be the source of something dangerous that can greatly impact our daily lives? We are talking about solar storms whose frequency increases drastically during solar maximum. Solar storms are intense bursts of energy from the Sun that can travel millions of kilometers through space and hit our planet. Solar storms occur when the Sun releases huge bursts of energy in the form of solar flares and coronal mass ejections, or CMEs. These phenomena send a stream of electrical charges towards the Earth at a speed of about 5 million kilometers per hour. Were it not for the protective magnetic field around the Earth, these charged particles could destroy all life on Earth. A solar flare is a sudden burst of energy from the Sun's surface, while a coronal mass ejection is a huge cloud of charged particles that is released from the Sun's corona. Scientists can predict when solar storms will occur, but they can't accurately predict the severity of the storm. The most severe solar storms can cause widespread power outages. Power grids are particularly vulnerable to solar storms. The electromagnetic radiation from a solar storm can induce electric currents in power lines, causing transformers to overload and potentially cause widespread blackouts. They can disrupt communication systems and damage satellites by overloading their circuits with a deluge of charged particles. In 1859, the largest solar storm on record, known as the Carrington event, occurred. It was so powerful that it caused telegraph lines to catch fire and created auroras as far south as the Caribbean. If a similar event were to occur today, it could have catastrophic effects on our technology-dependent society. Imagine what would happen if the internet was disrupted across the country, banking, the stock market, railway reservation and functioning of the railways, air travel, defense, government functioning, entertainment, everything would be severely affected. Life would come to a standstill. If satellites get disrupted, GPS, remote sensing, entertainment, communication, all would be disrupted. Even wars would be affected as guided missiles use GPS. We cannot afford such a catastrophe upon us. We have to be prepared. What is more, India has a rich array of satellites for different purposes, including our own GPS, abbreviated as NAVIC. All these national assets are endangered by the solar storms. This is where the role of Aditya L1 comes in. It will help us unravel the secrets of the different solar phenomena, enabling us, perhaps, to guard our assets in a better way and contribute to furthering human knowledge so that it benefits all of humankind. While solar storms can be dangerous, they also create beautiful auroras in the sky. Auroras occur when charged particles from the sun collide with particles in the Earth's atmosphere, creating colorful displays in the night sky. Solar storms are a reminder of the power of nature and the importance of being prepared for the unexpected. By studying solar storms, we can better understand the sun and take steps to protect our technology and our way of life. The Aditya Solar Wind Particle Experiment, aspects in short, and the Plasma Analyzer Package for Aditya, PAPA in short, are payloads specifically designed to study solar storms to be able to ultimately protect our electronic technology, which is the backbone of modern society. Aditya L1 is designed to perform cutting-edge science to unravel mysteries of Aditya, the sun. It is a pioneering project of ISRO that will push the boundaries of human knowledge and put India at the forefront. The huge amounts of data that will be collected by Aditya L1 will serve many young dedicated men and women who have invested their careers to understanding the laws of nature, to invest their intellect and skills and take the country forward. In the words of the poet from Bengal from the Renaissance period, Atul Prasad Sen, Bolo 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 shobe, shotobina benu robe, Bharat abar jagat shobhay, shrestho asona lobe. Which means, say in chorus amidst the accompaniment of hundreds of venas, that Bharat will again regain its supreme position in the comity of nations. Every little step, every success, every individual effort will take the country towards that rightful place. Let us celebrate it, let us take pride in it, and let us all contribute to it.